Hello. So in some previous videos, I've done some derivations of moments of inertia, but I thought that it'd be a good idea to conceptually go over what the moment of inertia actually is, which I plan to do in this short video. So first, I'd like to go over some common terms used in linear dynamics. That being that force is equal to mass times acceleration, and momentum is equal to mass times velocity. And from here, we can look at their rotational analogs. So the rotational analog to force is torque, which is r cross f, can commonly be equated to I alpha, where I is the moment of inertia and alpha is angular acceleration. Meanwhile, L, which is angular momentum, is the rotational analog to linear momentum, P. So L is r cross P, which is usually equivalent to I omega, where once again I is moment of inertia and omega is rotational or angular velocity. Um, so we know that alpha and omega are the rotational analogs of A and V, acceleration and velocity. And from that, you can gather that the moment of inertia I is the rotational analog to mass. So just as something that is more massive or has more mass is harder to push or lift, something with a higher moment of inertia is harder to rotate. And to give a clearer picture of this, we can look at what would happen if we had two disks at the top of a ramp. We'll give them the same radius and the same mass, but one will be hollow while the other will be solid. The hollow disk has all of its mass at the same radius, so its moment of inertia is mr squared, and the solid disk has a moment of inertia of 1/2 mr squared, which I've derived in a previous video, or you can look up. So because the two disks have the same mass and radius, the hollow disk will have a higher moment of inertia because it doesn't have the 1/2 term, and because of that, it'll be harder to rotate. Um, and the ultimate implication of that is that the solid disk will reach the bottom faster than the hollow disk. You can also sort of see this by looking at the form of rotational kinetic energy, that being 1/2 I omega squared. So even if two objects have the same rotational kinetic energy, um, if one has a higher moment of inertia I, it must therefore have a lower angular velocity omega, to sort of balance it out in this equation. So I hope that that provides a clear conceptual understanding of what the moment of inertia actually is, and I hope that you enjoyed the video. If you have any questions or suggestions for future videos, please comment below. Thank you.